Hi, I'm Don Box. I'm going to spend some time with you talking about what's going on in COM+. As you probably know, Windows 2000 is finally going to ship, and there's just tons of innovation that is there to take advantage of. And I'm going to spend a little bit of time with you trying to bring you up to speed on what's going on with the model, how it affects you as a person out there trying to develop code with all this stuff. You may know me from my work in MSJ. I write for Microsoft Systems Journal. I also wrote a few COM books that are fairly well known. And I co-founded a company called DevelopMentor, which is a research company that does a lot of work in distributed computing. We also offer short courses you might be interested in taking. Our URL is there. I have now satisfied the marketing requirements of this talk. Let's get on to the content. If you look at COM, COM's pretty straightforward. There are three basic ideas that permeate all of COM. The first real good idea that permeates COM is this notion of interface-based programming. And this means that we program in terms of abstract data types that we call interfaces instead of classes. And this is sort of a refinement of the way classic OO worked in the 80s. And it's pretty widely accepted as a good idea. And if you look at other technologies in this space, this is pretty much the way we do things. And COM was certainly there from the beginning. It's been a very dominant force in COM. Secondly, the second good idea is the fact that we build stuff dynamically, that a process that uses COM, a program that uses COM, is completely built at runtime. We're constantly dynamically loading components from here, there, the other place. And this gives us a lot of flexibility. It gives us a lot of good performance characteristics. It also allows us to do things like runtime extensibility. That is, having an application discover code that it didn't know about when it was built. Very interesting ramifications of having this. And these two good ideas have really been the core of classic COM. And if you've really looked at the literature over the years, these two ideas have permeated things. Around the time of Microsoft Transaction Server, or MTS, there's a third good idea that started to emerge, and it's certainly become much more pervasive over time, and COM+ really drives this home. And this third good idea is the fact that a developer, rather than writing tons and tons of code, declares what their needs are, declares their intent through declarative attributes, rather than through making API calls. And the idea is that by declaring your intent, the system can figure out exactly what it is that you need and provide it for you. And it's a really interesting model, and that's going to be really the core of what we talk about in these next couple of hours together. Now, let's just quickly do a level set so that we all understand what COM is. I'm not going to go off on a long diatribe about GUIDs and IUnknown, but it's just important that we all have a basic vocabulary that we share so I can get through this talk and that you can get through it too without your ears bleeding too badly. If you look at COM, it's based on this separation of interface from implementation, right? As clients, as consumers of someone's code, we program against these abstract data types called interfaces. These things are just signatures. They're just skeletons or prototypes. They have no concrete code. There's no statements inside of executable statements inside of an interface. Another really interesting aspect of interfaces is that they're polymorphic. That is, we program against a specification, and over time, we may actually wind up coding against different people's versions of that interface. And as long as we all agree on what the interface means, life works out great. So that's the programming model from the client perspective. As a component developer, we support interfaces by developing what are called COM classes, or sometimes called co-classes. And a COM class is simply a named implementation of one or more COM interfaces. And it's virtually all code. It really reflects the manifestation of your ideas as an interface designer. And this is the programming model. It's pretty straightforward. It takes a little while to get used to. But there's a lot of people out there doing it, and it's been very, very successful for a lot of projects that have come and gone. In terms of classes, the class is really just it's an implementation detail. It's something that the guy who writes the code has to know about. But in terms of the client, all the client cares about are the interfaces, and the classes are just the names of the code that he's going to go off and load. Now, here is my one brain dump slide of like the entire COM universe. People spend years trying to figure this out, and I'm trying to distill it in one slide. So let's see how successful I am. If you look at the blue block of goo at the top of this slide, that's something we call IDL. And IDL stands for the Interface Definition Language. This is the way components get described in COM. And IDL is this language which might look a little bit verbose and Baroque, actually. It's something that you get used to very rapidly. And most of these systems that allow us to do distributed objects have some sort of IDL that you need to, at least be conversational in, even if you don't actually write it yourself. Most of the tools nowadays hide a lot of the complexity of IDL behind wizards and other facilities in the interface, in the IDEs. But you have to be able to read it because it's everywhere you go in COM. It's very hard to imagine being a COM programmer that works even in scripting environments or Visual Basic, not being able to at least superficially read IDL. So this slide's just to get you used to seeing it. I know it might be shocking if you've never seen it before, but you'll get used to it rather rapidly. So there we go. If we look at that blue block, there are 3 things in it. There are 2 interface definitions. One interface is called iCalculator. The other interface is called iClearable. And notice that we just have descriptions of operations you can perform on objects inside of these interface definitions. There's no code, there's no executable statements. It just says, look, if I had a calculator, I could call this function called op that takes one parameter as input, and that's a long integer. It gives me another value as output, and that's that second parameter with the ret val. There's another interface called iClearable that says if I had a clearable object, I'd be able to tell it to clear. It's very, very simple. Don't worry about the details. The details aren't important for this particular discussion. It's when you write the code that they will come back to haunt you. At the bottom of that little blue block of IDL, we see something called a co-class, and that's a class. That's a named implementation of one or more interfaces. And that little description says there's this thing called adder. And if you were to create an instance of the class adder, it would support the interfaces iCalculator and iClearable. There you go. That's really all I expect you to be able to do in terms of reading IDL. Know what an interface is, know what a class is. If you look at the code fragment at the bottom in red, that's some VB code that takes advantage of this IDL. So assuming I've brought in that IDL somehow or another into my Visual Basic environment, which is fairly straightforward to do, I'd be looking at writing code like you see at the bottom. So notice I declare an object reference of type iCalculator. I bind it to a real object by using the VB new operator. And the VB new operator simply goes under the covers and calls the API function co-create_instance. It's pretty much the only COM API function we're going to talk about in this little discussion, simply because it's the center of the model. Co-create_instance goes out, loads the code from wherever it happens to be, maybe talks to a DCOM server, whatever, we don't know. All we know is that when this thing is done, we're holding a valid object reference that has an op method, as the IDL shows above. Because I might also want to tell this adder calculator to clear itself, I declare a second object reference of type iClearable, and I simply assign the one object reference to the other. And because they're of different types, this tells the VB runtime to go off and call a well-known COM method called queryInterface. And queryInterface just asks the object, are you also clearable? And if he says he is, great, we get back a valid object reference. Otherwise, in this case, an error will be raised, and we'll catch it somewhere else. Assuming that succeeds, we use the clearable reference to ask the object to clear itself. We then use the other object reference to tell the object to do some operation, in this case, add 35 to itself. And then we're done. On the way out, we set the object references to nothing just to clean up. But of course, we're in VB, and VB cleans up after us at all times. Now, I've thrown out a few words there. This slide really just has the vocabulary that I need you to understand. And a lot of these things we've defined already, so let's just quickly go over it. An interface, it's an abstract data type used by clients to talk to objects. A class is a concrete data type written by developers to support or implement one or more interfaces. Now, the term we haven't quite defined yet is an object. And a lot of people confuse class and object. I want to make sure you don't do that because it really makes these things confusing if you do. So an object is simply an entity in memory that supports one or more interfaces. And typically, it's an instance of a class. So classes are the things we write in our development environments, and objects are the things in memory that are usually instances of those classes. Those two terms are fairly well known in OO literature and pretty consistent with what you've seen out on the schoolyard, so to speak. The fourth term turns out to be a real can of worms. If you ask 5 developers that work in this field what a component is, you'll get 5 different definitions. All of them are, I guess, valid, but the definition we're going to use throughout these talks for consistency is the one that's on this slide, which is a component, is a loadable module of code, a loadable piece of code like a DLL, that exposes or implements one or more COM classes. And to us, that's what a component is going to be. The other four definitions are perfectly reasonable, but they don't apply in this talk. Now, no discussion of COM would be complete without this last term. And it comes up a couple of times in the talk, so let's just put it on the table. There's this thing called a GUID. And a GUID is simply a globally unique identifier. And it's just a big giant number. And we use GUIDs throughout COM and MTS, COM+, and all of these technologies to identify things. So anytime we have something out in the world that we need to identify, we typically attach a GUID to it. And for the most part, as a VB programmer, this stuff is buried in the plumbing, although it comes back to haunt you if you don't understand the basic idea of what it is. And they just turn out to permeate the runtime of COM, if not the programming model of COM. Now, COM can be used for two things. One thing that we use COM for a lot is to glue together a process. So we want to build a program, and we want to stitch together a bunch of DLLs and make them work together properly. And so we'll call this task one. And so as a component integration technology, COM provides the services like class loading, type information, type discovery, a few other various and sundry things that are useful for stitching together DLLs so that they can interoperate together well. And there's another thing we use COM for, and that's inter-process or inter-host communications. And in this respect, it's basically a glorified RPC technology. Now, here's the good news. We use the same programming model, the same technology, the same APIs for both tasks. And that's great news. Surface area of the technology becomes smaller because all I have to know is co-create instance. Co-create instance occasionally loads a DLL, and it's great. I'm gluing together a process. Sometimes it makes a connection to a remote server, and hey, I'm doing communications. That's the good news. The bad news is we have the same programming model and APIs for both tasks. And the downside of this is it's not always obvious to us as component developers which task we're in, what we're trying to do. And a lot of pain and suffering happens when we try to take a component that was designed for in-process access and then simply, flip a few bits in the registry and try to access it using DCOM. Basically, it's a bad idea. Likewise, if we design our components for distributed access, if we're using COM as an RPC technology, we're probably going to design interfaces that don't work so well for gluing together processes. Maybe they won't be very easily accessible. Maybe I can't get to them from scripting environments, a whole bunch of problems that can arise. And if you look over the history of COM, if you look at the practice, typically the better designed COM systems acknowledge the fact that COM is used for two different things and design various aspects around the task at hand. And there's there's kind of this adage that we use in COM, which is design two interfaces. One interface is great for programming, another interface is great for communication. And it's very, very difficult to write an interface that serves both tasks well. So we'll assume that we're always aware of this. I always like to tell a little bit of the history of COM in a COM talk, just so people have some context to associate this stuff with. The roots of COM can be traced back at least to 1988. There's a famous white paper, which you can actually dig off of the research site at Microsoft, that kind of was the seed work for COM, and you can see the evolution of COM right there in this one white paper. And if you look at it, a lot of the ideas in COM were influenced by things like Smalltalk and C++ in terms of the object model. And certainly the OSF distributed computing environment, or DCE, is DCOM. I mean, DCOM is really just a very thin veneer on top of DCE, as it turns out. Now, 88, the stuff started. 93, the public got its first look at COM as part of the OLE2 SDK, which was released in 93, although it went beta in 92. And the first release of COM was actually very, very usable. It had a couple of limitations. One limitation was it only supported local communications. So if you were interested in the second task that we use COM for, which was communications, it was kind of limited. You could only do it on one machine. Another limitation is it only worked on a very broken operating system known as Windows 3.1, which was 16-bit and very flaky and horrible and a bad nightmare that we all just wish never happened. And that was really the drag of the first version of COM. In fact, my own story is I was a Unix guy. I came over to do NT work, and I had to go back and learn about global handles and selectors and segments and all that stuff just to do COM programming. Fortunately, a year later in '94, Microsoft was nice enough to put COM support in Windows NT with the 3.5 release. And at this point, I was able to delete all of my Windows 3.1 CDs and go back to a normal, sane life. Um, and 3.5 basically brought us 32-bit support for COM. It also brought us something called the interface definition language, which was a sane way to describe the data types we were using in our COM programs. 95 brought a little bit more innovation, and that was the NT351/Windows 95 release of COM. Minor upgrade, better support for threading, and also they remembered to flip the optimization switch, so the performance was a lot better under 351. There's kind of a parallel track of history that we can talk about, and this is really the MTS evolution. In '92, the Viper project started, and the first artifact that we saw on the outside of this project was the Distributed Transaction Coordinator that shipped with SQL Server. It didn't ship with Microsoft Transaction Server because there wasn't really a visible Microsoft Transaction Server, but support was added to SQL Server to support distributed transactions that can compose with other resource managers. The work was started in '92. A lot of stuff happened though in '96 though. In '96, NT4 shipped. This brought us, of course, DCOM, which has been a very useful thing to have around. And also the security support and threading support got a lot better in NT4. '96 also brought us MTS 1.0, which was this framework for building distributed applications based on components. Right, a very radical idea at the time, very, very different from the conventional TP monitors that were out there. And in '98, the stuff got really usable. '98 brought us the Option Pack, which was just this conglomeration of a whole bunch of technologies. Version 2 of MTS, which was a lot better performance-wise, Microsoft Message Queue, and IIS. And all of these products work together in a really nice way. And this happened in '98, and that's history, right? Really nothing's happened since then, except a lot of betas have shipped. And fortunately, this year is going to bring us Windows 2000, which is kind of a culmination of a lot of other things. We should talk just very briefly about what MTS was. And notice I used the past tense here. The reason for that is I live in beta land. I usually don't use shipping software. I like to run stuff that's barely working. So betas are kind of been my way of life since I got into this Microsoft game. And as far as I'm concerned, MTS is done. It's over. And that's because as of Windows 2000, it's no longer a real entity. However, on NT4, it was a very, very important thing, which has been assimilated into the COM model, as we'll see soon enough. MTS was this programming discipline that said, look, we have servers, they have state, we have to be smart. We have to be very conscious and deliberate about the way we handle our state. And so MTS provided a bunch of infrastructure for doing state management. There were things like a common pooling model to help us unify resource reclamation. There was common transaction coordination, which helped us with concurrency management and error handling. And really the key of MTS was, rather than exposing 10 million more APIs, the MTS team decided to expose their services through declarative attributes. And this was just like the jewel of this model. And we'll see that this has become much, much more mainstream in COM+ in Windows 2000. So what is COM+? Again, if you ask 5 developers, you'll get 5 different definitions. Let's try and put some shape around it. Many aspects of COM development in general get better under Windows 2000. Windows 2000 is just a fantastic build of COM that everyone I know who works in the COM space is very happy with. Now, some aspects of COM development aren't going to get better until after Windows 2000. This is where the confusion comes in. The term COM+ has been attached to both what's happening in Windows 2000 as well as stuff that's happening after Windows 2000. Since I like to talk about stuff that has some hope of being usable to you in the near future, we're going to focus on the stuff that's shipping in Windows 2000 only. The innovations that come after that, we'll talk a little bit about, but very briefly and very, very soon. The majority of this talk is based on stuff that is only shipping in Windows 2K. So, 3 areas of refinement in Windows 2K. The most important one is the integration of MTS and COM. As we'll see, there's no more 2 variations on a technology. We have one technology, it's called COM+, and it has the best of MTS and COM, and hopefully none of the bad parts. There's also, the second refinement, is there some new MTS-esque services that apply to, some of these services apply to everyone, some of them apply to people who only have certain problems, We'll take a look at a lot of these along the way as well. There's also some improvements to the remoting infrastructure, which we're not going to spend a lot of time on in this talk, simply because they apply primarily to plumbers and not to application developers. Now, the former two of these refinements, that is the MTS integration work and the new MTS-esque services, are often referred to as COM+. And throughout this talk, if you hear me say the word COM+, that's what I mean. Some things that aren't shipping with Windows 2000 but often are thought of as COM+, are things like the new type information infrastructure. Today, we just have a mess. The IDL compiler makes these things called type libraries. There's fidelity problems. There's reliability problems. It's functional, but by no means what we want to have. A lot of stuff was written early on in '97 about how this was going to be fixed. Those fixes aren't going to ship with Windows 2000. Sorry. I'm as heartbroken as you are. Hopefully we'll get them soon after. A new class loading infrastructure that eliminates the need for things like iClass Factory and a few other pieces of goo that we'd like to lose. Those didn't happen either for Windows 2000. Also, a lot of people wanted user-defined interception, and certainly a lot of the early writings on COM+ would lead you to believe that that was going to be happening. And it probably will happen, but not in Windows 2000. So the stuff, for instance, that you've read in the Mary Kirtland articles in Microsoft Systems Journal, a lot of that stuff is post-Windows 2000 work and just didn't make it this release. However, what we did get was pretty good. Right? The MTS integration is just a godsend and solves so many problems. And that's what we're going to really focus on throughout these talks. So let's look at the three refinements to COM in Windows 2000. First is the MTS integration work. In NT4, we had MTS and we had COM. And very often there were two ways to do things, the MTS way and the COM way, largely because they were developed more or less independently. The beauty of NT5 or Windows 2000 is that these two things are now integrated. And basically we just have COM, or we'll occasionally call it COM+, but basically the COM way is the way we do things. So the way we create objects is the COM way, co-create instance. Right? The way we pass object references around is the COM way, the right way, the simple way. Some of the MTS stuff, like the additional circuit infrastructure, all of those things just fall off. And we have a much, much more unified model. Some benefits are it's an easier thing to think about. There's less cognitive load about, do I call this function or that function? More importantly, the performance gets better and the stability gets better. Simply because we don't have a thing on a thing, it's just a lot cleaner model, so much better. Also, because the cost of entry to using some of these services is lower, a lot of people who aren't writing OLTP-like applications are going to be drawn into this programming model of using things like context and attributes. And so it's just a really wonderful thing, and we'll do a lot of discussion about this stuff throughout this talk. Here's kind of the evolution. If you look at NT4, we had this layer cake, and at the bottom layer we had the COM runtime, right? And the COM runtime gave us things like class loading and the DCOM, the remoting infrastructure. The MTS team came along and built this thing called the MTS Executive, which layered on top of OLE32 and gave us things like context, concurrency management, transaction management, a lot of really useful things that the COM team, it just wasn't their charter to do back in 88, 89, 92, what have you. Now on top of this, every tool vendor has to build a certain amount of integration infrastructure to thunk their programming abstractions that they have at their programming language down to the way the COM runtime, if you will, expects things to work. And so we see, a lot of replication of effort between the Java VM, which is used by Visual J++, the VB runtime, which is used by the VB product, and the ATL team also has to do a fair amount of work to get things to thunk down to the way COM works. It's all doable, and we don't really think about it as developers, but you can see there's a lot of layering going on. This was the NT4 snapshot. If you look at Windows 2000, you'll notice that two of the DLLs merge into one. And that basically we get our context, concurrency, and transaction management from COM, rather than from the separate product called MTS. Notice, though, that a lot of the language integration stuff is still being done by the tools. In the post-Windows 2000 timeframe, it all becomes one big happy family. One DLL gives us everything, a lot of unification and folding in of functionality that a lot of the tool vendors are doing, all happens now down in the runtime. It's a very happy story. But again, it's post-Windows 2000. So that's the integration story. Another refinement that's fairly interesting is that there's some new services that ship with Windows 2000. Here's kind of the laundry list. We'll talk about a few of them that are more important as we go along when we have some more context to put them in. But here's kind of the laundry list. IMDb gives us a transaction-aware cache, very useful thing, very hard thing to build by yourself. We also get a few refinements to the transaction management infrastructure that solve some really critical limitations that we had under MTS. Things like the compensating resource manager and bring your own transaction. We'll talk about both of these later on. Q components are yet another way to do MSMQ programming that has a couple of advantages that we'll talk about later on. Then we have things like load balancing in the event service, which if they match your scenario, do a wonderful job. They're not quite as difficult to get around as some of these other things that are provided by the system. And we'll focus on the stuff that's much more difficult to do yourself, like IMDb, throughout the talk. Now, the third refinement in Windows 2000 is some new stuff in the refinement architecture, in the remoting architecture. There have been some holes. A lot of people have been fighting NT4 over various things. A lot of this stuff is fixed. Not everything, but a lot of things are fixed in NT5. We have a better threading story, a lot more sane. A lot of the bad dream of apartments is somehow deprecated, although works in NT5. This is a really nice story. We now have call cancellation. We have a facility called Handlers for building smart proxies. We have a better endpoint management story, so we can have a little bit more success at breaking through firewalls, although it's always going to be difficult. And of course, security, a lot of refinements, so the challenge of getting security to work is now more challenging, but at least we have a lot more options, which is a good thing. If you've been deploying DCOM apps, you know the challenge that is security. We're not going to talk about most of these refinements, mainly because they apply to only a small subset of the COM development community. People who do low-level plumbing work are just like frothing at the mouth for this stuff. But there's a vast number of COM developers who could really care less about some of these innovations. So if you're interested in them, you know where the resources are, and we'll point to a few at the end of this talk. So, inhale, exhale. What's all this stuff about? Well, if you look at how COM works, a lot of the innovation and evolution of COM is driven by people who do distributed application development, right? And a lot of the services that we see coming out of the COM team have been to help people build distributed applications. Now, there's this family of technologies, DCOM, MTS, MSMQ, COM+, that the folks in Redmond have decided to call Windows DNA. Now, to some people in this world, Windows DNA is this mantra, it's this architecture, it's this infrastructure, this guiding beacon of truth. To others, it's yet another architecture term for whatever Microsoft is shipping this year. The reality is actually somewhere in between, right? Yes, it is a architecture term, although it has survived 2 PDCs, so it actually may stick around for another year or two. But it also has some good ideas in it. And what I want to do is, rather than go through the architecture spin, look at the good ideas that kind of permeate this model that we have, that a lot of people call Windows DNA, and I'm happy to call it that too, as long as Microsoft does. If we look at the overall architecture, it's based on some fundamental assumptions, and these assumptions drive some fundamental principles that dominate the way we build things. Let's look at the assumptions first. Well, here are the 3 big assumptions. First assumption is we have multiple users, right? We're building distributed applications. We want multiple users to take advantage of this stuff. These users are going to live on different host machines from where the code runs. They're going to access the code via the web or maybe via a private network, but that's not always the case. And the user interface, the user experience of all this stuff, is going to be presented either via a browser or maybe via a custom application, a form-based app that you write in VB. That's still fine. If you want to write an MFC app, go in peace. Happy to do it. But that sits over on the client machine. Second assumption is that we're going to have distributed processing spread across multiple server machines. And this brings up the need for things like load balancing, dealing with locality of reference. We do it because we want concurrency and parallelism. It also gives us fault tolerance, right? If the whole world runs on one box and that one box crashes, it's not a very happy story. And the third assumption is kind of a reality check, which is, bad things happen, right? Our application state, maybe not the running application, but the residue, the artifacts of the application, have to survive things that happen every day, like application errors, system crashes, blue screens of death, an occasional service pack update, or the eventual Y2K power grid meltdown. The idea is, when the power fails, and 20 years later, when we bring the computers up, we'd like the state of the application to have been retained on the hard disk, so that we can go back and carry life on as it was back in the year 1999. So those are the assumptions. There are three principles that kind of dominate the programming model, and we'll see these throughout the talks. Principle number one is we want to put the application logic on server machines, not on client machines. And there's a lot of reasons for us wanting to do this. One of them is the client machine may have a very low bandwidth or low reliability connection to the network, in which case we want to minimize the traffic that's involved with the client to the actual data. Also, the server machines often have better locality of reference with where the data lives, which is very, very often in a database. Because we're putting things in databases, we often want to be very sensitive to the cost of database connections. And by putting most of the logic over on the server machines, we're basically multiplexing access to the database through what people often call the middle tier. And this has a lot of performance benefits simply because we're not using as many database connections. We can share them a lot better. There's a lot of other resources we can share a lot better as well by doing it this way. Another really important issue is that when we have client machines, often we don't have a lot of control over the security context, right? Random user buys a new laptop, puts the Win98 CD in, sets up an admin password, whatever, and God only knows what the security world looks like over there. And if we care about our data, if we care about the way our applications work, we often want to have a much more controlled security context. So by doing most of the work back in the middle tier and further back, we have a much better lockdown on the security story back there. We don't have to worry so much about JRandom clients coming in. The second principle that really dominates the model is that transactions are the core. And as an old-time COM OO person, I resisted the move to transactions, but since then I've spent a lot of time with this architecture, and the transaction is the thing. The transaction so permeates the programming model that you have to embrace it, and if you don't, you're really not going to take advantage of what's available for you. Transactions turn out to be a great solution for concurrency management. I know a lot of you probably played with multi-threaded programming, and hey, go in peace. But a lot of the primitives we have from the OS just aren't very good for doing, really high throughput on concurrency management. Transactions turn out to be a lot better. Also, transactions obviously give us pretty good protection against crashes, right? We have the obvious atomicity of a transaction, which we'll talk about in the next talk. But they give us a fairly good error recovery model. Transactions turn out to be a great way to compose work from multiple parties. But one of the interesting aspects of using transactions is it says, look, to protect things, I need to put things under control of some sort of transactional resource manager, which means we tend to put the majority of our state inside a database or something slightly more exotic. But it turns out we don't keep too much state inside the actual objects that we write. And this is a very big departure from classic OO, or even from some of the things like traditional Corba-based designs, right? So the whole idea of programming with transactions and having transactions permeate, it's the way our model is designed, it's the way the runtime is designed, and if you embrace it, things go really well. If you try to resist, hey, resistance is always futile. The third principle that we have to deal with is the fact that we're going to stitch together our server applications using COM components. Right? Remember the two tasks that we use COM for: stitching together an application and doing distributed communications. Right? We're going to use COM pervasively for stitching together processes. Right? However, the communications aren't always going to be done using COM. We're going to use COM sometimes. There's a lot of applications where COM is great for communications, but we're often going to do communications using other technologies. The primary way clients are going to access our components is not going to be via DCOM, but rather it's going to be through HTTP, right? Because the web turns out to be a very proven way to get clients to connect to the resources that they want, right? We can use MSMQ, it has some benefits. We can also use DCOM, but the primary way we're going to do it is through HTTP. The server-side components themselves, however, are going to communicate with one another using DCOM all the time. DCOM turns out to be a great component-to-component communication technology. We'll also use data access protocols to get to our databases because that's what they expect. To date, there aren't too many database servers we can go buy off the shelf that accept DCOM calls. They like to have their own proprietary data access protocols, and hey, go in peace. Thank God we have OLEDB to abstract away some of the grunge of that. Now, one observation I'm going to make right now, and we're going to make later on, is that connectionless protocols generally scale better. I know there's a lot of discussion about stateless programming, and I don't want to get into it because it's just a can of worms that I refuse to engage on. But if you look at what really gives us scalability in these systems, it's connectionlessness-ism, right? It's the fact that we want the flexibility to dispatch work on the fly to different machines. And the way we achieve this is by using connectionless protocols like HTTP and MSMQ. So, Don, this is all very interesting, but how do I do it? So there's all this technology. How do I actually go off and use COM+ to develop an application? And I wish I could say it's very simple, but the idea is simple at least. The devil's always in the details. It's 4 basic steps, right? Because we know we want to use transactions, we know we need to keep our state, the state of our application, inside some sort of resource manager, and typically that's going to be a database. So step 1 is model the durable state of our application as some sort of database schema using the database tools of your choice. Doesn't really matter what you use. Most commercial databases today talk to COM+ just fine. SQL Server obviously is one solution you could use. There's others, of course, as well. Step 2, model the protocol of the application, that is the interchanges that happen in the application, as COM interfaces. So we have the schema, which represents the state, and we have the interfaces, or the protocols, which really model the behavior. And it's really taking classic OO design and turning it on its ear. But it turns out that OO and distribution are 2 very, very different things. And doing it this way is very, very happy in terms of distribution. Step 3 is once we figure out how we're going to lay things out, we go off and write a bit of code. We write it as DLL-based COM components that implement the interfaces, that is step 2, in terms of the schema, which was step 1. And really, our components just act as manipulators that do fancy things to our databases. And this is the way we build the applications, and it works, it scales, it's a really, really good thing. Finally, as we're building the code, but especially after we build the code, we're going to take our components and drop them into an environment that we call COM+. And along the way, we're likely to utilize COM+ services where they apply to us. Obviously, transactions are a big service we care about. We'll also be using a lot of COM+ security stuff, take advantage of concurrency management, and so on and so on. So this is the idea. This is kind of the technique we use, right? Now, don't be fooled. It's not going to take you a day to do. It's not going to take you a day to understand. But these are kind of the repetitive ways we go off and do these things. Now, let's talk about some technology. I think we're done with the precursor part of this talk. In general, once you pass the age of 30, you no longer want to go off and write your own thread scheduler, file system, or window manager. And you're pretty much happy to take advantage of the platform. Now, in the past, the platform was exposed to you via explicit APIs. You'd make API calls, take advantage of the system. It was great. That was the past. COM+ is moving towards a different model. A platform's still going to provide tons of services, and that's great. But rather than making explicit API calls to take advantage of them, we're going to take advantage of them implicitly through these things called interceptors. And interceptors are simply middlemen that sit between the consumer of an object and the object itself. And these interceptors are system-provided objects that do all of the heavy lifting of the service prior to dispatching the call. Now, let's talk a little bit about how interception works. To provide these runtime services that we care about, the system has to intercept every single invocation against your object. So if the client wants to call a method, he has to go through the interceptor first. The interceptor is going to pre-process the call, then dispatch it to you. And when you're done, you return control to the interceptor, not to the client. The interceptor, in all likelihood, is going to perform some post-processing before returning control to the client. And in fact, in certain situations, for example, in security checks, we may never even dispatch the call to the actual object. The interceptor will look at the call, say, hey, this guy's not allowed to do that, e-access denied, and it's all over. We don't even see the call in our object. Now, for all of this magic to work, the interceptors need to know what our interfaces look like, which means we have to have some sort of type information that we expose. Now, all of the COM tools you're likely to use emit type information that makes COM+ very, very happy. So you're going to be fine. Now, an interesting observation, if you've done any MTS work whatsoever, we also had interceptors in MTS. The difference was in MTS, they were tacked onto the side. They were in the MTS executive and not integrated into the plumbing, which meant we had this terrible function called saferef that you had to be aware of. You had to call it from time to time, and the rules for calling it were well known, but you had to call it. The beauty is in COM+, things like saferef, fall off like a tail we no longer need. simply because the interception is built into the runtime and every part of the model knows about it. Now, here's a problem. We have a little bootstrapping problem. We want to have all the work done in the interceptor, not in our component. We just want to provide the specific part of our application that's app-specific in our components. We want the real heavy lifting to be done in the interceptor, which means we don't want to write any code, or we want to write as little code as possible. So how do we configure the interceptor without writing code? Right? We don't want to have a story where we have a meta interceptor that configures the real interceptor. So to bootstrap this whole system, we configure the interceptors using declarative attributes. And the idea is, if my component wants to take advantage of some of these extended services that we're going to be talking about, I have to indicate this declaratively. And COM+ introduces this term called configured components. And a configured component is just a class that has these extended attributes that control the way the interception works. Now, COM components are always written as DLLs, and if we want remote activation or out-of-proc activation on the same machine, we use surrogate processes, which are these little containers that are provided to us by COM+. We don't write our own exes anymore. This is one of the first departures from, classic server development. Now, if we look at how configured components work, the idea is we have the mapping of our class names, which of course is a GUID, onto the file name, which is where our component lives. There's also a place where we have to store all of these extended attributes, like whether I want a transaction, what kind of security checks I need to have performed. The details of where these things are stored has varied from MTS to COM+. And in general, we don't care where they're stored. Rather, we access all of these things via something called a catalog manager. The catalog manager is just a COM component that manages the registry and any other configuration databases that live on our machine to make sure that we just drop our component into the Explorer interface or through some scripting interfaces onto the catalog manager. And the catalog manager controls the attributes and makes sure that they're made available to the COM+ runtime. Now, under COM+, it's a much better story than under MTS. If you've done any MTS work, you're probably aware that MTS would just hijack your registry entries and redirect everything to the MTS executive. This is no longer. Rather, we leave your standard COM improc server 32 registry entries intact, and rather layer all of the extended attributes in a totally different part of the file system. And Co-Create Instance is smart enough now to go look at this other part of the file system to see what services you need and insert the appropriate interceptor. Right? Much better, much cleaner, much faster. Another interesting aspect of this is the catalog. The COM+ catalog is a transactional resource. So changes we make to it can be protected by transactions as well. This is another new thing that we get in COM+. Now, if we look at the catalog is segregated into these things called applications. And if you're an MTS person, you used to know them as packages, but we call them applications now. Get used to it. Every configured class belongs to one application, and we use applications to group shared classes together so that we can have some shared attributes that configure the entire set of classes. The way we configure things doesn't necessarily correlate to the way we package things. So I might have 2 DLLs with 5 classes in each one, but I might partition them into different applications for a variety of reasons, usually for security reasons or for fault isolation reasons. When we build a COM+ application, which is really just a collection of configured classes, we have a choice of whether we deploy it as a library application, in which case all of the components load in the creators process, or as a server application, in which case all of those classes load in their own distinct private surrogate process. Here's kind of an explanation of the disconnect between the way we package components, which is shown at the top of the slide, and the way we deploy components in applications. And notice that there isn't necessarily a one-to-one correlation between where the code is, which is in a DLL, versus the way we deploy it and the way we configure it, which is the application. Right? And we have flexibility using the COM+ Explorer to rearrange these things. And given the limitations of this media, I can't break into a spontaneous demo right now, nor can I break into a spontaneous song. So I'll spare you both of them. Go run the demo yourself and sing a little song about COM+ if you like. So, what's stored in the catalog? Well, the catalog just keeps track of all of the classes that have been configured. And it keeps track of the attributes that are associated with these classes. And the attributes are used to configure the interception services that we're going to get back from the system. Now, the set of attributes is fixed for now, Hopefully in some post-Windows 2000 world, we'll be able to add user-defined ones, but that's not the way it is now. Rather, the set of attributes is fixed to correlate to the set of services that are provided out of the box with Windows 2000. Now, it turns out that pretty much anything in our world can be attributed. We can attribute applications, individual classes can have attributes, interfaces on a class can have an attribute, or a bunch of attributes, and methods on interfaces on classes and applications can have attributes. So there's really, a fairly nice layering model here. And at any given moment, we look at what method am I invoking, what interface is it on, what class is it associated with, and what application I am in. If we take the union of all those attributes, that gives us some idea of what's going to be happening inside the runtime and inside of our method. We set these attributes using the Explorer. It's now called the COM+ Explorer. It's just a fancier, more friendly, and polite version of the old MTS Explorer. It now says welcome and thank you, and a few other nice things as well. And hopefully, someday we'll be able to set these attributes in our development environment. To be frank, a lot of these attributes, your average Cable Monkey MCSE has no business setting, right? There's nothing in the MCSE curriculum or training program that tells people whether or not my component needs a transaction, right? That's really something I, as a developer, want to be able to set. And I'll be able to set it in the IDEs eventually someday, but certainly not in the current generation. Here's kind of a laundry list of all the attributes that are available. I'm not going to bore you by enumerating them, by talking through each one of them. I'll call out a few of them, which is like the application type. Notice we have library versus server. What I do want to call out is notice that some of the options are underlined, some of them are not. Again, in many ways, COM+ is just MTS version 3. And so you'll see that a lot of the old stuff from MTS has just seeped back up into COM+. The underlined options were what was available under MTS, and everything here is available under COM+. And notice that MTS had a somewhat more limited view of the world. Previous slide talked about what we can attribute on an application. This slide shows us the attributes that we can apply to classes, interfaces, and methods. And again, the underlined options were what was available under MTS. And all of these options are available to us under COM+. We'll see a lot of these attributes as we go along, so let's just leave it till we get to them. Let's talk about one attribute which is very useful, comes right out of the box, very applicable to everybody. We can all relate to it. Right, this idea of configuring components and letting the MCSEs of the world have a little bit of control over the way our application works, because they do have a role after all. It's not just to put firewalls between us and what we want to do. Often we want to allow these guys to work on our applications and somehow to configure them. And of course, they can set the canned attributes that Microsoft provides. It'd be nice to have our own. Well, we almost have one of our own. There's a universal backdoor into the catalog manager that allows the system administrator or you as a developer or whoever to go in and have one individual attribute that can be stored in the catalog, saved and deployed across the network with your application, and passed to every instance of your object. So as we'll see on the next slide, we have the ability to pass one single configuration string into all instances of the components, and this is done through the Explorer, and it's stored in the catalog. This string gets fed to your component via an interface called iObjectConstruct that your component then goes off and implements. And you'll be fed a COM object that contains the initialization string that you can then suck out and parse however you want. Now, what do you put in this string? Who knows? Who cares? COM doesn't care. It just takes the string that's stored in the catalog and gives it to your component. You might want to put in XML. You might want to put in a ODBC or OLADB initialization string or some other application-specific string. That's up to you. This slide shows you the back door. If you look at a class-by-class property page, under the Activation tab, you'll notice that there's an Enable Object Construction feature that allows you to specify any old string you want. And of course, it's up to you to document how you're going to interpret this string, but that's your job. If you do this, your object is expected to implement the interface iObjectConstruct, the IDL shown down there. It's just got one method, construct. You'll be given an object. At every time an object is created, you'll be given this constructor object that contains whatever string was stored there. You just suck it out by pulling out the string from that second method there and interpret it to your heart's content. Do whatever you want. Now, one nice thing about the feature we just looked at, as well as all of the other attributes that are part of COM+, is that we have the ability to configure an application on our development desktop right here and take all of the settings that we've made, as well as all the components that are needed to make it work, and serialize it out to the file system for mass redistribution. And the way we do this in COM+ is we simply select the application, tell the catalog manager to export it into something called an MSI file, which is a Microsoft installer file. And this MSI file contains all of the attributes serialized into some internal binary form that we don't really care about, as well as the actual DLLs, type libraries, proxy stub DLLs, whatever else it took to make my DLL, my application work. All of that stuff gets serialized into a single double-clickable file that I can just drop onto the file system of another server machine, double-click, and instantly that server is now available. That application is now available on that server machine. We also have the ability to export client-side configuration information, things like the remote server name entry and any marshalling or remoting bits that are needed to make my application work. And this comes out as a second kind of MSI file called an application proxy. And these MSI files can just be deployed through the Active Directory or through file copying or what have you. And even through the catalog manager. I can go through MTS or COM+ Explorer rather, and configure a remote server machine, drop my MSI file over there across the network, configure a bunch of servers without ever getting off of my chair. And of course, because this is all done through the catalog manager, I can also do it with script. Here's kind of a view of what we get. When I export a COM+ application, I get an MSI file. It contains all the serialized attributes, as well as any component DLLs and any type descriptions, like type libraries or proxy stub DLLs, that are needed to make this thing fly. Single double-clickable file I can just drop onto any other server box. Now, let's take a little bit of a look at the internals and kind of baby step our way into it. Remember I mentioned that there were two kinds of COM+ applications, library applications and server applications. Library applications are used for components that are utility components that will be used by a lot of different server programs. So we want them to be able to be efficient and load directly into whoever creates them. So library applications really solve the, I've got a class that I want every other application to be able to use. The way we solve that is we put it into a library application. The idea behind library apps is they always load in the creator's process, which means you have to be on the same machine. And what happens is co-create_instance just says, okay, I'm loading a DLL, and I see you have these needs that you've expressed through your attributes, and an appropriate interceptor will be configured and returned to the client. Now be aware that we may or may not be protected from concurrent access, depending on how we're configured, but for compatibility with the old world of MTS, if we drop our DLL into COM+ Explorer, we get serialized access right out of the box. So don't worry about thread management or any of that other, unpleasantness. So here's a little animation that shows how it worked. Client makes a co-create_instance call, which of course is exposed by ole32.dll. Co-create_instance is now smart enough to look for the extended attributes, load your code, but also create an interceptor that corresponds to what your needs were. And notice that the client gets back a pointer to the interceptor, not to your actual object. And that interceptor is where all the transaction management, security management, concurrency management, and everything happens. Your code does the application-specific stuff. Server applications turn out to be the norm, and this is typically what we build in COM+. And a server application loads in its own distinct server process, and all of the classes in a single server application run in one process. And if we have two server applications, that means there's two processes running, one that contains the classes from the first app, the other process contains the classes from the second app. Now, we use server applications because they have better security support, they support remote activation, and they give us a way of isolating component faults. So when one component crashes, it's not going to bring down every other application on the machine, which is a good thing. We want to keep them running. Now, here's some interesting good news if you're an MTS person. The server applications are now loaded by the classic COM surrogate, which was called dllhost.exe. And dllhost.exe is now the surrogate we use for everything. There's no more mtx.exe, which is what we used to use under MTS. Another interesting bit of good news is that we have 3 gig support. So simply by clicking a checkbox in COM+ Explorer by setting a catalog attribute through the scripting interface, I can indicate that my components are safe for 3 gig support, which allows me to have a little bit more capacity for supporting more clients. Here's a little animation that explains how COM+ server applications work. You'll notice the client calls co-create_instance, but this time, even though there's an inproc server 32 entry that says, hey, the code's in foo.dll, co-create_instance also checks the attributes and says, whoa, stop. This thing is configured to run in a server application. I don't care that there's an inproc server 32 entry. we're going to load it in its own distinct surrogate process, which is, of course, called dlhost.exe. Once we're in dlhost.exe, the COM+ runtime goes off, loads the server code, or the component code, creates the object, and we get a proxy and stub, which is the interceptor in this case, that performs all of the services. And most of the services really happen over on the server side of this little conversation, hence the plus on the stub picture there, right? Again, the client gets back an object reference. It looks just like you, but all the services happen before we get to your object. Notice that both in this picture and in the previous picture, raw references to your object don't happen in terms of the client. Client gets interceptors, and that's the way we want it. And I know it feels like we're putting a layer between you and your client, but that layer is very important. And to be frank, raw access to COM objects seemed like a good idea in '93, but over time, I don't know it's going to be such a good idea. So this is a pretty good model. We get a lot of benefits from having it this way, and that's the way it works. Now, let's scrape into the interceptors a little bit more. As we see, COM+ provides us with advanced services if we say that we're willing, and we say that we're willing through these declarative attributes. The services are implemented by the interceptors by pre- and post-processing every call. Now, what do the interceptors do? I mean, ultimately, what the interceptors are responsible for is establishing a runtime environment for method invocation, so that when my method code runs, the world is exactly as I described it in my attributes. Right? Very, very important observation. I indicate through attributes that I need a 4-bedroom house with a white picket fence and a big screen TV. Right? Now, of course, those aren't real attributes, but you get the picture. It's up to the COM+ world, the COM+ infrastructure, to ensure that every time one of my method calls runs, it's running inside a 4-bedroom house with a white picket fence and a big screen TV. Right? And we call this runtime environment that gets set up by the interceptors a context. Now, a context is simply a group of objects within a process. And we use context in the COM+ programming model to group together objects that have similar needs. So everybody who needs a big house with a white picket fence may run in the same context. But more importantly, we use context to separate out objects that don't see the world the same way. If one object needs a house, the other object needs a condo, we want to put them in different contexts. Right? So we use context both to group together similar-minded objects and to segregate dissimilar-minded objects. And some interesting observations is an object in space. Remember what a COM object is. It's an instance of a class. An object lives in exactly one context, and that context corresponds to how the component was configured. And because we want to build server processes using COM, we wind up having lots and lots of contexts inside a single server process, inside a process in general, in fact. Here's a little picture. Notice the process on the left, process X, pretty simple, has a couple of objects. They both wanted similar things, so they got to run in the same context. Process on the right, a little bit different. Right? Process on the right had some objects that had one set of requirements, and some other objects that had a different set of requirements, so the COM+ infrastructure put them into two different contexts to make sure that when the method calls on the objects in the middle context ran, the world looked one way. And when method calls ran on the objects on the far right, they looked a very different way. Right? Very, very important concept. We use context to segregate components, and it's the interceptor's job to enforce this. Now, we've got these different contexts in the process. It's likely that one object in context A is going to want to talk to an object over in context B, and we want to allow that, but at the same time, we want to make sure that the interception services run the appropriate way. So we access objects across context boundaries using interceptors that we sometimes call proxies. And throughout these talks, I'm going to use the term proxy and interceptor interchangeably because ultimately they are, at least semantically. And it's the job of the proxy/interceptor to expose the interfaces of the actual object. However, upon invocation, it's the job of the interceptor to somehow perform whatever magic is required to change the runtime environment from where we issue the call to what the object expects. Right? That may involve acquiring a new transaction. That may require not using a transaction. It may require performing security checks, doing concurrency management. God knows what it's going to have to do, right? But it's the job of the proxy and the proxy/interceptor to do all of this stuff for us. This picture really says it all. We have a process. We have a bunch of contexts inside this process. And notice that as we hop from context to context, we do it via these interceptors. And these interceptors are tuned to the delta between what one context looks like and what the other context looks like. And they just do whatever is required to make sure that when object B, A, or C are running, that during their method invocation, if they look out, they see a world that has an appropriately colored sky. If B said, I want a blue sky, he sees a blue sky. If A said, I wanted a red sky, A sees a red sky. It's the job of the interceptors to enforce this. So, I keep using this hand gesture as I talk about contexts. There's a reason for that. Turns out that contexts are real, living, breathing things that you can touch as a COM programmer. And the contexts are exposed to you via COM interfaces. And that at any moment in time, your COM+ component can reach out and feel the walls around it, which are really the walls of the context. Now, the way this works is, for every thread, and I'm not going to talk about threads too much here, but for every thread in the system, there's a piece of thread local storage that refers to the current context. And the primary job of the interceptors is to make sure that this reference to context is always set up appropriately. So that at any moment in time, my component can just reach up, because every method is executed on a thread, that somehow the thread space has been set up so I can reach out, and this little pointer or reference is somehow pointing to the appropriate context. And this context contains things like my transaction. It can contain some information about my concurrency management, my security management, etc. Right? Everybody knows where the context is, and we all know how to reach out and touch it. Right? Now, that's the simple story. Slight complication. Sometimes inside of a method call, the world I'm looking at is the house. It's the world I've described through declarative attributes, and it sticks with me from method call to method call to method call. We call this kind of context object context, because it stays with the object for the duration of the object's lifetime. There's a second kind of context, which is a little bit different. Every time a method is invoked on my object, COM sets up a second kind of context called call context. And it turns out that I can see both sets of walls. The inner walls are the method context, or the call context, and the outer walls just behind them are the object context. And in general, I just talk about it as the context of my method call. And that's pretty much the way we'll describe things. But technically, and you'll see it as you start to program in this model, we have object context, which is for the stuff that sticks around across method calls. That's where your transaction goes. And we have call context, which is stuff that's transient on a per call basis. That's where a lot of the security stuff goes. Here's kind of a little diagram of how it works. You've got your object there in green and tan. Underneath you, you've got your object context. That stuff sticks around for the lifetime of your object. But every time we invoke a new method call, there will be per call context as well. And we can access both of these contexts through a couple of API functions, which we'll talk about very shortly. In fact, on this slide. So there's two API functions you need to know. CoGet call context reaches out and gets the per method context. And CoGet object context reaches down and gets the method invariant object-wide context that sticks around for the duration of my object. These two functions return COM object references, which we can use then to influence how our component works. So we set up a bunch of declarative attributes. They control what our context looks like. But often we want to do things like reach down and grab the transaction and do something with it. Or check, is the caller who called this method in a particular named list of users that I might want to check security against? So we have access to our context. For historical reasons, the object context has a couple of call-specific methods, but the good news is the object context interfaces have been refactored in COM+ in a much more sane way. So while there's an interface which we'll mention once in a while called iObject Context, that's the MTS interface, still supported, still works great. People who are targeting Windows 2000 only or Windows 2000 and greater should probably get off of that old interface because it wasn't that well designed, or wasn't as well designed as some of the newer stuff that we'll see in this talk. So here's a picture that shows the object model. Notice we have an interceptor in front of our object. The interceptor is really responsible for setting up the object context and the call context. We access these two pieces of context by calling the two APIs shown here. CoGet call context gives us the transient stuff. CoGet object context gives us the object-specific stuff. Here's a diagram showing what interfaces are exposed. And notice that the object context supports the interface iObject Context, how appropriate. But it's kind of deprecated. The ones that are in italics are kind of, they're still supported, but they're MTS, and we want to get off of them as soon as possible. The non-italicized interfaces are, the future, and that's the stuff that's in Windows 2000 and greater, and that's really the stuff that if you're developing stuff that doesn't have to run under NT4, you should be programming against. Here's a little bit of IDL. The CoGetObject context function turns out to be the core of this programming model, and it's where we do most of our work. And notice that it's a simple function that returns an object reference, and the reference it returns, the one we care about the most, is iObjectContextInfo, and this is really where a lot of the action is in the world of COM+. And notice that we have access to our transaction, we have access to the identifier for our context. We also have access to something called an activity, which we'll talk about very, very soon now. An interesting cultural fact you should know about, the interface name is iObjectContextInfo. However, for a variety of reasons, primarily VB programmers don't like to type lots of characters, when written or typed, the interface is typed context.info, but when spoken aloud, it is literally spoken iObjectContextInfo. So you don't embarrass yourself amongst your COM+ cronies at a bar. Don't ever say the context.info interface. They'll laugh you out of wherever you're at. Say iObjectContextInfo, but when you type it in VB, just drop the iObject. It is invisible, but always spoken. So here's a bit of code. We have a component that, let's say I've declared that I want a transaction, and if I don't have a transaction, I'm going to be very unhappy. Of course, as we know, the COM+ Explorer can be launched by any cable monkey. And here's some paranoid code that ensures that, JRandom MCSE doesn't come along and take away my transaction declaratively. So notice that my code, which is called paranoid method, simply reaches out, touches the wall by calling getObjectContext, and calls the isInTransaction method. And if I don't have a transaction, that means I've been misconfigured, somebody did a bad thing. I'm going to just raise an error here, in this case, unexpected. Otherwise, I go off and do my work, knowing full well I've got a transaction that's protecting all the work I'm doing. A lot of kids ask, where does context come from? Right? It's one of these, creationist questions that we all have. My son asks it of me a lot. And rather than tell him the hackneyed old story of, well, a mommy context and a daddy context who love each other very much, and, the rest of that story, I usually just tell him the facts, the basic biological facts of context. And here they are. Objects get associated with a context at creation time. So when the client calls co-create_instance, that's when the context is created, and in general, that's when we associate the object with the context, although we'll refine that a little bit later. So the way the algorithm works is, when co-create_instance is called, we have a couple of factors. It's being called from some context, because we always have context in COM+. At any given moment, we're running in some context. So at co-create_instance time, we look at where are we at, that is, what kind of universe am I living in now, and we compare that to the declarative attributes of the target class, the thing we're trying to create. And if the requirements of the target class match where I'm living now, hey, we don't need interception. It's great. We load the DLL, and the code and the object run inside the context where we call co-create_instance. There's no interception. It's classic Brock-Schmidtian load library style COM. If, however, at least one attribute in the target class is not compatible with where we're at now when we call co-create_instance, co-create_instance says, look, I can't put the object in that environment because he said he needed something different. So in that case, what happens is co-create_instance typically creates a new context, although occasionally we'll find an existing one. Co-create_instance will create a new context, create the object in the second context, and return to you an interceptor so that we have some way of talking to the object, but the object's requirements are still met. Because the object said, I can't run in the kind of world you're creating me from. And that's how these things get created. Now that's true for configured components. Interesting question is, what about non-configured components? What if I don't have any attributes? What does co-create_instance do in that case? Well, it turns out it's a very simple thing. If you don't have requirements, if you do not have attributes, if you're a non-configured component, that is, you haven't been dropped into COM+ Explorer, well, hey, we assume you can run anywhere. We assume you don't care about transactioning or security or any of this other stuff. And in general, you simply get loaded in the context of whoever creates you, which means, in general, we never create interceptors for non-configured components. So that the model is, client calls co-create_instance against a configured component, creates a new context. Right? That component creates a bunch of other components that are not configured. Things like data access components like OLADB or ADO. Those things aren't configured. They tend to run inside the context of the guy who creates them. And this turns out to be necessary because we want our data access components, which are really just loadable code modules, to be able to access the runtime environment of my heavier weight application component. And that's the way the model works. So in general, configured components, we wind up creating a new context for. Non-configured components just run wherever they're created from. Now, a context in memory has properties. So if we think about it, we have these attributes that we store on disk that control what our context looks like. But ultimately, at runtime, they're manifested through a context object which has properties, data members, if you will. And these properties inside the contexts flow as we do work, right? And the call context tends to flow as we make method calls. There's this term called causality, which just says I've got a chain of method calls throughout the network. A calls B, calls C, calls D, and then they all return. That's a causality. And call context, things like security information, tends to flow at call time through a causality. Object context, which is really the important set of context. Those properties tend to flow when we make new objects. So co-create instance is responsible for taking the context properties of where I'm at now and presenting them, giving them to the new context, and giving the new context the opportunity to share all of the properties I have. So if I have a transaction, when I call co-create instance, my transaction is presented to the new object. And modulo configuration issues, my transaction is going to flow through to the new object. So that in essence, we share the transaction. The work I do composes with the work he does. So again, object context flows at object creation time. So when we call co-create instance, the properties of the creator flow through to the new context. And here's a bit of interesting information. This is the way the model has been designed from the beginning. The problem was, under MTS, co-create instance didn't know about context. Co-create instance was a totally separate thing from this world of MTS and context-based programming. So in the old days, there was this method we had to call called iObjectContext create instance. This function is now deprecated because co-create instance has gotten a lot smarter in Windows 2000. Right? We can still use the old MTS-style create instance function. It's obviously supported for grandfathering reasons. But in general, new code doesn't need to worry about it. New code can call co-create instance and it just works. So this slide has a great animation, at least in my opinion, that illustrates how this stuff works. So look, the way this story works is we've got an object, we've got some code running in a context that's going to call co-create instance. That context has properties. In this case, this component was configured to run in a blue, dry, and fuzzy runtime environment. Now, when this guy calls co-create instance against another class, co-create instance looks at the properties of where we're at now and compares it to the attributes of the target class. And if they're not compatible, we're going to get a new context. So let's assume that's going to happen. We get a second context. Now, here's the fun part. The properties in the creator's context are just presented. They're given. The co-create instance says, here are my properties, take them if you will. And based on how the attributes have been configured, some of these properties will flow through to the downstream context. In this case, the blue property will flow through because the second class, hey, he's fine running in a blue environment. However, we're assuming in this little example that the second component needed to run in a wet runtime environment as opposed to a dry runtime environment. So co-create instance says, okay, this is probably the reason we gave you a second context in the first place. I'm not going to flow through the dryness property. We'll give you your own wetness property. Fuzziness, hey, it looked okay to you. You weren't declared any other way, so we let it flow. Now the object runs in the second context. The thing we get back from co-create instance is an object. That object runs in the context that's blue, wet, and fuzzy. Of course, the creator gets back an interceptor. And it's the job of the interceptor to deal with changing the runtime environment from blue, dry, and fuzzy to blue, wet, and fuzzy. In this case, all the interceptor has to do is moisten the runtime environment. And of course, get a towel out and dry it back up by the time we return to the client. Now, I don't know how to break this to you. Blue, dry, and fuzzy are not real properties. These are not actually exposed in this or any known future version of COM+. But they turn out to be very, very simple concepts that are fairly effective at understanding this. The obvious properties we're going to use are things like transactions. right? Transactions are a great example, and we'll look at a variation of this picture when we talk about transactioning. Okay, well, let's talk about a concrete property. One thing we don't want to be in the business of is manual concurrency management, right? Trying to deal with, multi-threaded access or multi-user access. The kind of plumbing we have to build to do that correctly turns out to be very, very hard to build. And it's not as simple as using, say, a Win32 critical section. That's great for programming in the small, but for building, large distributed applications, that strategy melts down really, really fast. So we're lucky. COM+ gives us a lot of concurrency management abstractions. First one we're going to look at very quickly is this thing called an activity. So what an activity does is it protects my object from concurrent method invocation. So if I configure my component to run inside of an activity, then the runtime, the interceptor, will ensure that there is never more than one thread invoking calls on my object at any given time. This means I am no longer on the hook for worrying about concurrent access to my instances. It's going to be done by the runtime, and it's going to be done in an extremely efficient way under Windows 2000. The activity model is just the primary way we do concurrency management throughout all of COM+, throughout all of COM under Windows 2000. All that stuff with apartments that you used to hear about, it was a bad dream, right? We still have them in Windows 2000, but we don't use them for concurrency management anymore. They have a very, very deprecated small role. We're not even going to talk about them in this talk. They're just not important, right? The activity is the way we do concurrency management in Windows 2000. Now, how do we get an activity? Well, how do you think? Declarative attributes. There's an attribute named synchronization, and I set the synchronization attribute to indicate whether or not I want an activity, that is, whether or not I want call serialization, as well as how I want my activity to relate to my creator's activity. Right? Sometimes I want to make sure that while my creator is in use and being locked down by this interception framework, my object could still be accessed. Right? Sometimes I want that, in which case I want a different activity from my creator. Sometimes I want to make sure that while my creator is being accessed, I'm locked down too, so you can't get to me. In that case, I want to share the activity. So co-create instance checks the synchronization attribute and puts the new object in either no activity, the creator's activity, or a new activity. This slide here shows the possibilities for the attribute, which are not supported, supported, requires, and requires new, and indicates what my expectations are, what's going to happen at runtime when we call code create instance, which is the only place this attribute is inspected. So here's the question. Will my context and my object be in an activity? Well, the answer is shown in this table, and the answer is if I'm required or requires new, I'm always going to be in an activity. I never have to worry about call serialization. If I'm marked not supported, concurrency is a total thing I'm happy with. I would like concurrency. Let all the threads come in and party on. I'm butch enough to take it. Supported is kind of a strange case, which says I'll share the lock with my creator if he's got one, but if not, don't create a lock on my behalf. It's there for completeness. It's likely not to be used that much in most COM+ development. Requires and requires new are really your bread and butter settings. And the second column indicates whether or not I share the activity with my creator. And it's right there on the slide. You can look at it yourself. But just notice that the primary distinction is required versus requires new. If I'm marked requires, I'll share the lock of my creator if he has one. If I'm requires new, I'll never share the lock of my creator. I have my own private lock, which means while a method is executing here, another client could be invoking a method on me. And it's an option. It's there if you want to use it. But required is pretty much the mainstream one. Notice also that if you were writing MTS code, this attribute existed, although it was invisible in the user interface. The only one of these attributes that was supported for MTS was synchronization equals required. Here's a little picture that kind of demonstrates how this works. Notice that context C and D live in the same activity, which means that once a thread starts executing a method on any of those objects, all of the objects in those two contexts are going to be locked down, and no one else is going to be able to get in. Notice that on the left side of the picture, we have a couple of contexts, A and B, that are also in the same activity, but in this case, they live in different processes. Now, in an ideal world, we would like for a network-wide, zero-cost lock to just make sure that while I'm in an object in context A, no one can talk to objects in context B. Unfortunately, Microsoft is subject to the laws of physics, and that kind of lock just isn't possible. So given that, while the model supports an activity spanning multiple process and host boundaries, physically we're only going to lock things down on a per process basis for efficiency. However, the good news is if an object in process A creates an object in process B, which then creates a third object back in the original process, the activity flows, so at least the two objects in one process get to share the lock. So there's some reason for doing it, but don't fool yourself into thinking we have some zero-cost, low-calorie, great-tasting locking mechanism that's just going to be great. We have something that's very, very reasonable in the single process case. And as we'll see later on in the next half of this talk, we use transactions to do the locking in the broader scale. Now, how do activities work? It's pretty easy. The activity data structure has two things we care about. It has an identifier called the GUID, which is there. You can actually get it through the iObject Context Info interface. But the thing we really care about is that there's an exclusive lock that's in the activity data structure. And what happens is, at interception time, when we enter a new activity, we try to acquire the lock, if it's there. And it's an exclusive lock, which means only one user can get it at a time. And we hold that lock while we dispatch the method call. When the method call returns to the interceptor releases the lock, letting the next guy get in. This picture shows a nice animation of how the thing works. You'll notice that call comes into an interceptor. The interceptor notices that we're in an activity, tries to acquire the lock. We then dispatch the call once we acquire the lock, and we may be held there for some very long period of time while someone else is doing something to the object. Although in general, this won't be the case because of the way we program things. Once the lock is acquired, we dispatch the call. Call gets dispatched. You return control of the interceptor. The interceptor says, okay, we're done. We release the lock and return control of the client. When we release the lock, next thread is allowed in. It can start accessing our object. So notice that at any given moment in time, only one thread will ever access our object. Very, very important. Now, one last topic before we wrap up this part of the talk. And that's this topic called just-in-time activation. Remember I said when we talked about where does context come from, I mentioned that basically at creation time, when co-create instance gets called, it creates a new context and associates an object with that context. And then I put the little parenthetical comment, mostly. And here's where the mostly comes in. In general, that's the way it works. Client calls co-create instance, we create a context, and at that time, we associate an object with that context. However, for a variety of reasons, which we'll look at, your object may want to have more flexibility in terms of how it controls that mapping. And if you want this kind of control, we say that your object supports a feature known as just-in-time activation, or JITA. And the idea is, JITA is a declarative attribute that you turn on and off using COM+ Explorer or some other lower-level device. And if at co-create instance time we discover you support JITA, we have a few more options. One thing that happens with JITA-based objects is we postpone our initialization until the first method call. That is, we don't necessarily associate the object completely with its context until it's needed, until the client issues the actual work request, which is its first method call. Additionally, we have the opportunity to detach our object from a context and associate it with a different context, or associate different objects over time with a given context. This gives us a lot of flexibility, which it turns out we need for transactional programming, which we'll talk about in the second half of the talk. JITA objects typically implement another interface called iObject Control, which is used by the plumbing to let you know when you're inside of a context and when you're detached from a context. Now be aware, if you enable JITA, which by the way is on by default when you deploy in COM+, inside of your language level constructor and your language level destructor, you don't have context. So if you're expecting to have things like having a transaction, you can't count on it. It's not guaranteed. In fact, in many cases, you won't have one. So here's the JITA, here's the iObject control interface, right? You're expected to implement iObject control. Two methods that are important. Activate says we've just dropped you into a context. Deactivate says we're pulling you out of the context, okay? Can be pulled, we'll talk about very briefly later on. Here's the life cycle. Your object is created. This happens at co-create instance time. And notice that in your constructor, there's no context. It's only at the first method call we let you know you've now got context by calling your activate call. We then dispatch a few method calls in the runtime. When your object goes away, we first tell you this is your last chance. Kiss your context goodbye. This is through the deactivate call. And after that, we release your object and it goes away. Now, COM+ has, this actually was very commonplace in MTS. COM+ has some really great innovations in this front, though. We have a couple of new features which are under the umbrella term of object pooling, but technically there's two sub-features of this. One of them is resource governing. We have the ability in COM+ to say, don't allow more than n number of instances of my class to be created. And this is a great way to throttle the number of clients that can come into your server process. We also can have a low watermark that says, make sure that at any moment in time, there's always at least this number of instances created, even though they're not in context, right? Now, to use the low watermark, right, the COM+ infrastructure is going to just be creating objects, not on behalf of co-create instance, but because it says, you said you wanted n objects around, we'll create them. This is great if the initialization of my object is really expensive and generic, that is not tied to a particular client. Now, that's one feature, very, very useful. Another somewhat related feature is, if my initialization is so expensive and so generic, maybe I'd like to reuse that and amortize that across a bunch of activations. This is where the recycling feature comes in. And recycling is often confused with object pooling, but technically it's just a facet of object pooling. And object recycling is where the can be pooled method comes in. And when we deactivate an object, right after we deactivate it, we say, can you be pooled? That is, can you reuse your initialization? And if you can, instead of destroying the object, we put it onto a free list and then activate it in a different context at some point later on. Here's the settings in COM+ Explorer. You can go play with this in your own little hands-on demos that you're going to go off and perform. It's very, very straightforward. Here's a picture of the life cycle, and really the important thing to note is, after deactivate, rather than just destroying you, we can reactivate you later on in another context. Some caveats you should be aware of. Number one, you can't do this in Visual Basic, at least not Visual Basic 6, because of some context neutrality issues, which will be ironed out in some future version of Visual Basic, which I'm sure will ship shortly after Windows 2000. To paraphrase Bill Clinton, it depends on what your definition of shortly is, but that's another story. Here are all the requirements for making this work, but the really important thing I want you to take note of is look at the bottom bullet. Recycling is only going to benefit you if your initialization is expensive, generic, and reusable. Right? This is not every object known to man. This is a very small percentage of the objects you write. One last sub-feature here. If I support JITA, the context supports something called a done bit, which says, my object is done. I don't need to be attached to this context anymore. Take me away from this context, and the next time a method call comes in, attach a new object or perhaps a recycled object into this context. This is called as soon as possible deactivation, and it turns out to be very critical for transactional programming. Here's a picture of how it works. The context keeps a done bit. Inside of my method, I set the done bit, and when I return control, I'm deactivated. And the next time a method call comes in, a new object is created. Now, the interesting COM+ innovation on this front is that I can now set that declaratively in the COM+ catalog. So I can say this method always deactivates the object. This has some nice benefits in as much as I can reduce the code size, especially when I'm doing transactional programming. So to wrap up, COM+ exposes services through interception. We control our interceptors through declarative attributes that we store in the catalog. These interceptors really live to set up a runtime environment called a context. We saw that contexts are used to group together objects that think alike and to separate objects that don't think alike. We saw one context property called an activity, which we use for call serialization. Here's some resources. You might check out the May 99 issue of MSJ. There's a couple of interesting articles in there. A variety of other resources that you can read for yourself and go chase down. Hopefully the second edition of my book will ship early in the fourth quarter, but it should ship sometime in the fourth quarter. It'll definitely beat the context architecture to death if you didn't get enough of it here. Anyway, thanks a lot.